So last year, the big graph we looked at were quadratic functions. Or the name of the graph of a quadratic function, do you remember? What did we call it? Parabola. Yes. Okay. We can stop a little bit. Let's go back here. Okay. And what we did is we took the most basic parabola, which was, and I might as well graph it here, which was y equals x squared. How did we graph y equals x squared? Where, like, what was the point we always started graphing? 0, 0, called the vertex, right? For a parabola, we call it the vertex. And then it looks like this. Or it could be upside. So, but then, I won't say that yet. And then what we did is we had equations that had extra numbers in them that told us to move the parabola around and to possibly stretch it and to possibly flip it. Well, when we move parabolas, left, right, or up, down, okay, that is actually called a transformation. We call it a shift or a translation. You're shifting left, right, you're shifting up, down. Okay, and we did those last year with parabolas. What else did we do? Another type of transformation that we did, we flipped them. Okay, and we flipped them vertically. If they were up, we flipped them down if there was a negative in front of the x squared, right? This year, we're going to add horizontal flips. Okay, we did vertical flips. What happens if you flip it this way? Okay, but we'll get into that later. We also did stretching. If there was a number in front of the x squared, it stretched this parabola, depending. Okay, if it was a number like 2, 4, 6, 8, it made it longer. If it was a fraction between 0 and 1, we compressed it. Okay, that's another type of transformation. There's 3 types of transformations that we're going to look at in this unit. And it's going to be shifts or translations, which we're going to do first. Then we're going to do stretches. Then we're going to do flips. And then we're going to combine them all together. But the thing is that we're going to go beyond just parabolas, because we can take any graph and do transformations to them. Okay. So what are some of the ones that we've already looked at? Well, in grade 9, really, possibly even before that, and in grade 10, we looked at linear. Y equals x looks like this. It's a diagonal line through 0, 0. Linear or lines. Quadratic, kind of a combination of a U-V shape. The most basic one started at 0, 0, and then it curved up on either side of the vertex. Towards the end of grade 11, we did absolute value. When we saw those, they looked like V's. Because remember, we graphed the line and flipped part of it up to make it look like a V shape. The most basic absolute value function has its, we could call it vertex at 0, 0, and then it's a V shape going up into quadrant 1 and quadrant 2. So it's pretty similar to quadratic. And then we looked very briefly at these at the end of last year, these rational ones where there was actually two pieces to the graph. We'd have one section like this and one section like that. And the most basic one, this point would be 1, 1. This point here would be negative 1, 1. But then we also added something to these graphs. Do you remember what else they contained? Asymptotes, yes. These two sections never touch the x-axis. So we drew a dashed line that represented the horizontal asymptote. They also never touch the y-axis. So we draw a vertical line that represents the vertical asymptote. So that's a completed rational graph. Okay. Why keeps doing that? Okay. I've already mentioned this, a translation. A translation is when we move a figure left, right, up, or down. In other words, we take every point on the graph and we shift it the same amount to the left, right, up, or down. And we saw these last year. When we dealt with quadratics, x squares. What happens when there was a number at the end? Did it shift it? How did it shift it? No. Up or down. If it was positive, it went up. If it was negative, it went down. So if it's after the x squared, it's shifted 2 units down. If it was inside with the x squared. So we put parentheses, we opened up a set of parentheses and put the 2 in minus form inside. That means it shifts 2 to the right, because remember, it's kind of the opposite, because it was always in subtraction form. So if it's minus, it actually shifts to the right. If it's plus, inside the parentheses, it actually shifts to the left. So this shifted 2 units right. How about this next one? 4 units left. Because if we were to write this in subtraction form, we would get x subtract negative 4 squared, because 2 minus is equal to plus. We always want it in subtraction form. So if we put it in subtraction form, this is actually negative 4, which tells us to the left. Finally, this is a double shift. Yeah. Shifted 2 units right. One. So that's kind of review. We can apply the same reasoning to other types of functions that we already know. So let's look at y equals absolute value of x. Well, y equals absolute value of x goes like this. This is y equals absolute value. Notice the points that it goes through. 1, 1, 2, 2, 3, 3, 4, 4, etc. Why? because if you plug 1 in, the absolute value of 1 is 1. If you plug 2 in, the absolute value of 2 is 2. It's also on this side, negative 1, 1, negative 2, 2, negative 3, 3. Why? Because when you plug negative 1 in and take its absolute value, you get 1. Absolute value of negative 2 is positive 2. Okay? So this is the basic absolute value graph. Given what we just did on the last page, how do you think you'd graph A? Take every point on this one and shift it 1 to the right. Because it's inside the absolute value, isn't it? If it was outside, that means we'd go up or down. So this tells us shift, and I'll use it, actually, I'll use a different color. Shift 1 unit right. What are we shifting 1 unit right? We're shifting, actually, we're shifting root x 1 unit right. So take every point and look like this. And this is y equals the absolute value of x minus y. What does the next one, B, tell us to do? Yeah, take the purple one, the absolute value of x, move all the points 5 down. So we're going to shift absolute value of x 5 down. All the points for the entire graph. So going back to the purple one, take each one and go 5 down. And that's going to look something like this. And that's y equals absolute value of x minus 5. And so for C, I'm going to take the absolute value of x, the original one, the purple one, shift it how? 4 left, 3 down. So from here, we're going to go 4 left, 3 down. And this is y equals absolute value of x plus 4 minus 3. I can do that with any function. I could take the linear ones, the lines, and shift it around just by putting a number inside with the x or afterwards. Okay? I could shift the rational one. So because I can shift any line, any type of function, no matter what it goes to. Well, what do we call any type of function? Y equals f of x. Okay. So let's say we've got a function here called f of x. I have no idea what its shape looks like. I don't care. Okay. All I know is I'm taking this and I'm moving it 5 units to the right and 8 units up. What would the equation look like if I moved it 5 units to the right and 8 units up? Okay, so how would we write that? No, it's not an absolute value. We don't know what this function is. It's just called f. So parenthesis x minus 5, close it, right? Because it has to be inside the function. So this means take that function f of x, move it 5 to the right, and to move it 8 up, put a plus 8 on the end. Yeah, so no, we're not talking about a specific, we're not talking about a quadratic, we're not talking about an absolute value. We're just talking about some function. I mean, like, it could look like this. It could look like this. We have no idea what it looks like. All I know is that if I want to shift it to the right, I have to put that -5 in parentheses with the x. And if I want to move it 8 up, I got to put a plus 8 on the end. So what would this one look like? Y equals f of x plus 6 in parentheses minus 7. See if you can finish the remaining 2. Very similar to the previous 2. Because this is something that we're going to do with a lot of these remember I said we're going to look at a lot of graphs this year. We're going to do 2 big things with them. When we get the function, how to graph it. Or if we're given the graph, how to come back and write the function. Okay, that's a lot of what we do this year. What would this one be? Y equals f of x minus 10 in parentheses minus 4. And this would be y equals f of x plus 1. Moving to the left, so it's actually x minus -1. Okay. So you can see how shifts or translations work. I don't use the word translations too much. I call them shifts. And shifts are either horizontal or vertical. If the number's inside a function, it's horizontal. If it's at the end, it's vertical. Okay. Here's another example where we're given the function. This is f of x. Okay. So this is what f of x is. It's kind of a combination of 2 segments and an array that goes on forever. I have no idea what the specific equation of this function is. I don't care. I'm just calling it f of x. Okay. If I were to create a new function, and if it's a new function, I got to use a different letter, so I call it g of x. I'm going to take function f and add 3 in parentheses. What does this tell me?
3 to what?
So that means I got to take the red one and move everything 3 to the left. So we just used the graph to do this, right? So this tells us f of x, 3 left. And then I've just replotted it. So 3 to the left here. Notice I'm using the points that I'm given on f of x. 3 to the left here, and then they connect like this. 3 to the left here, and they connect like this. 3 to the left here, and they connect like this, and then it just keeps going up forever. So that's function g of x. Okay. So we just use the graph and kind of do, you're kind of doing it mentally and just redrawing the graph. Another way you could do it is something called mapping notation, where you take points on the original graph, like the points here, 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 and here, are all four of those points, okay? And then you write the new points on the transformed graph. So for this one, what you would do is, okay, any point on the original graph, x, y, I'm going to create a formula to find every new point on the transformed one, or the translated one in this case. What does this tell me to do? Move it to the left. And if it's left, that's x, right? So doesn't that mean take every x and subtract 2? Because we're moving it left. So the formula for the x coordinate of every new point is take the x coordinate of the original and subtract 2. The formula for the new y coordinate is take the original one and subtract 1, because we're moving every one down. So this is called mapping notation, because I am mapping from one function to another. So I just rewrite all the points that I've given on the original function that I picked. -3 minus 2 is -5. 0 minus 1 is -1. That would be the new point. 0 minus 2 is -2. 3 minus 1 is 2. 2 minus 2 is 0. 3 minus 1 is 2. 3 minus 2 is 1. 4 minus 1 is 3. So plot all these points and connect them as you go. So -5, -1, -2, +2, connect. -2, 0, 2, connect. 1, 3, connect. And then you can see on the graph that it just goes up forever. Now you may ask me to say, well, that seems a rather long way to do it, when you could have just sort of done it like you did A, where you kind of did it in your head. You're right. And that's okay. Okay? For ones like this, that's okay. But the reason I'm showing you this now is we're going to use this for more complicated ones. Because you don't have to write this down. Because if I give you, let's say I gave you that original function, f of x, and I said, okay, we're going to create a new one called p of x. And p of x is going to look like -1/2 f of x minus 1, sorry, f of 3 x minus 1 plus 7. Okay. We're eventually going to be doing ones like this, but there's a lot more transformations going on here. Right now, if you look at this, you can probably tell me that you take the original function and you're going to move it 1 to the right and 7 up. Because of these, right? Because you know these. And actually, you might be able to tell me a couple other ones. This tells me you're going to flip it vertically. Okay, and what? Sorry, I'm not. Will it? Oh, sorry, yes, yes. This is going to stretch it vertically, and it's actually, because it's a fraction, going to press down and cause it to open up or stretch out like this. Okay. This we haven't done yet. We've done vertical stretches. Can you imagine what this might be? A horizontal stretch, which we haven't done yet. So you can see there's a lot of stuff going on in this one. It's kind of hard to do it in your head. This is where mapping notation becomes very handy. Because you just create a formula for all the new points and then just plot them and graph. Okay. Okay, just to wrap up. We don't necessarily have to use this. You can if you want. So here's what I mean. So what we did is I gave you functions. I gave you an original one. I gave you a transform one. We graphed it. This is working backwards. Okay. I'm telling you that f of x, the black, is the original one. And it's getting transformed to this. Okay. So what we need to do is we need to come up with the equation. And actually, I'm going to skip this. We don't even need this. How much is it shifting horizontally from black to red? Just horizontally. 5. You need to tell me direction. 5 to the left, right? Yeah. And how could you tell that? We'll just pick a point on the original. See where the corresponding point ends up on the transform. So move 5 to the right. 5 to the left, pardon me. So if it's moving to the left, that means h is -5. If it's moving 2 up, that means k is +2. And notice that when we plug it into this, because this is our transformation formula, when we plug x minus -5, it becomes plus, which makes sense because plus tells us to move to the left in the equation. So we get f of x minus -5, which becomes +2. That would be the equation. Okay, so we talked about one type of transformation, the shifts. Okay. And there's 2 types of shifts, horizontal, left to right, or vertical, up down. So if there's a number on the end that we call k, that is a vertical translation. If k is bigger than 0, the graph moves up. If k is negative, less than 0, the graph moves down. And notice I put that it moves down the absolute value of k. Because if it's -4, we don't say it moves down -4. We say it moves down 4. And that's why that's there. If we've got a number inside parentheses with the function, that is a horizontal translation. If x is bigger than 0, that means it's positive. So that means it's going to be like x -4, because h is 4 there, x -7, because h is 7. That means it moves to the right. If x is less than 0, -4, but when we plug it in, it becomes -4, which is +4, which tells us it moves to the left. Okay. Tis. Okay.